Today's notes? No. Today's notes are not DIY notes. Yesterday's notes. Well, technically yesterday's notes were not DIY either. I had a video, and we watched that video. Were you here yesterday, Cynthia? No. Okay, yeah. So yesterday, if you weren't here yesterday, there's a video on the home page. You can watch that and fill it in. Fill in your notes from that. Well, I don't feel bad that I can't remember if you were here since you can't remember if you were here. All right, we're going to go ahead and get started on today's notes. That is a 5.6 continuous compounding. So we're computing, since you're going to learn how to compute interest in an account, but it's continuously compounding. What does it mean? What does continuous mean? Do you have your Chromebook, Kamari? He's going to keep it? Okay. Okay. Send in, Kamari. Pick up your notes if you didn't pick them up on your worksheet for today. Okay, what does it mean for something to be continuous? Ezra? Constantly, non-stop? Yep. Is there a limit? I can't see. Is there a limit to how many times it will happen? Not by definition, right? How could you calculate something if it never ends? Anybody know? Well, irrational numbers have non-terminating decimals, right? They kind of never end, right? Square root of 7 is an irrational number. I think square root of 7, I'll put it on the calculator. We know we're computing it. We're never going to get an exact answer unless we just write the square root of 7, but we can see a decimal version of it, an approximation. What does infinity represent? Forever. Kind of the same as continuous, right? We know pi is an irrational number. The digits to the right of 3 are infinite. They go on forever, non-repeating pattern. They never stop, right? So 3 point never gets to 4. 3.14, you know, it approaches and approaches and approaches and never stops. Imagine you're walking across a room that is 64 feet wide. You must travel half the remaining distance at a time. Model this below. This is my model. I don't know how y'all are going to do it, but this is my person here. Oh, I'm going to have fun. I didn't do this earlier in the day. Jamie. Okay, we're going to walk from here to there. This is the wall. I went through and marked the halfway mark, approximately. So this is halfway. We walk from here. We're approaching the wall right here. That's the wall. We're trying to get to the wall, but we're trying to get in the wall by only walking half the distance each time. So what happens? That's what we're going to look at. Half of 64 is 32. So we stopped here. Now we're going to go half again. That's about 16 feet, right? Now we're going to go half again. That's 8 feet. We're going to go half again. Right here is half. 4 feet. I'm going to go half again. 2 feet. I'm going to go half again. 1 foot. I'm going to go half again. 1 half. Now, I don't have any more room for dots, right? But distance is not there's no mark to mark distance. If I go walk from here to the wall, it's 9 feet, right? This is 8 feet. There's no mark to mark that. So I can't mark any closer to the wall here because I'm using this big old dot. But this is 1 foot, now I'm cutting it in half. Now we're half foot away from the wall. Now we're a quarter of a foot away from the wall. Now we're 1/16th, 1/32nd, 1/64th. I can't keep illustrating that because mine's going to go away. But in theory, you keep having something. Am I ever going to get to the wall? Never going to get to the wall. We could touch the wall. We'd be sitting right on top of the wall practically, but in theory, if you have something, you would never get there. A real mind blower. We can have an infinite amount of numbers and get a finite sum. So we could add two irrational numbers or an infinite amount of numbers and never get a finite sum. We would get a finite sum. So 64 feet is a finite amount, but it could be the sum of an infinite number of halves of that, right? So the question was, can you add an infinite number? Well, we're just going to explore infinity. You can kind of see here. So let's just start with that. Everybody go to Canvas and open your Desmos calculator. I do want everybody to be on there. So everybody's going to pull up the Desmos calculator. I got you on GoGuardian, so I'll know some of you don't want to do it, but we're going to do it. Pull up your Chromebook, go to the home page, and pull up the Desmos calculator. Somewhere I know you can't do that. You've got your Chromebook right now, so you can just watch. Okay. Number 1 says, complete the table below using the following function. F of x equals x squared plus 3 times x plus 5. You see a table. They give us a list of inputs. X's are our inputs. F of x are our outputs, right? So we're going to go to our calculator. Let's zoom mine out. And we're not going to enter f of x equals, right? We're going to start with x squared. Our first x we're going to plug in is 100. So it's 100, and then the squared button is right here, the a to the second power, plus 3 times x, so 3 times our first input of 100, plus 5. We should get 10,005. Anthony, darling, Schmookum, go to the home page and go to your calculator. Albert, the home page and go to your calculator. Oh, hey, see, the beauty of the Desmos calculator. We know how to mistake. I can do a different thing on our table, and we can find that mistake. Here we go. It was a happy accident for me. So I'm pushing this Desmos calculator, and that is one of the reasons. I forgot the 1. So there we go. That's what I forgot. So 100 squared plus 3 times 100 plus 5. So it's easy for me to compare with what I'm supposed to be plugging in. So we're looking kind of at the relationship, what this is going to look like. So we're going to keep plugging in. Beauty of that Desmos calculator. Now my input, I want it to be 1,000. I can just go over here and add a 0 in both spots. So now it's 1,000 squared plus 3 times 1,000 plus 5. Can't see what I've got. And it's 1,003,005. So you guys put in 90,000. I should see everybody putting 90,000 in for the input, and you can just edit the equation you have in there right now, or the expression you have in there right now. Just click on the parts that you need to edit. You're putting that in there. 1,000, type in 1,000. Type in 1,000. I'm sorry, not 1,000, 90,000. We're on 90,000 now. Type in 90,000, Albert. And then getting squared. So to square, oh, right here. To square it, you hit the A to the squared button. Gonna hit that. Yep, that button right there. Plus 3 times 90,000 again. So type in 90,000 plus 5. $90,000. Okay. 90,000. No comment. No comment. Okay. Squared plus 3. All right. Silence says, Maddie, put your phone away. I didn't say what, but I looked up for a phone and I saw your phone under desk. 3 times 90,000 plus 5. What'd you get? What'd you get, Keith?
8.100270001 times 10.
Nice.
Wait.
All right, 90,000
Okay,
plus 3 times 90,000 plus 5. You're supposed to plug it into the function, guys. I did. We literally did say that. Literally did say that.
okay, right?
We've already done functions before in here, you goobs. You guys know. Inputs are plugged in for the x's. You people know this. We can't forget everything we've done up to date every time we use it again, okay? We've got to review some recall here. The x's are in the x column. We're writing the y's in the y column. They're giving us the inputs. We have to put the inputs in the calculator. Not only that, I showed you on the calculator. I'm literally putting it in the spots there, right? Kid's right. You guys put in put in 900,000 everywhere there's an X. Once again, this should have told you that because we learned how to plug in and evaluate functions given different inputs, and that's what we're doing here. So we're plugging in 900,000. Loving my Decimus calculator where I just add me a 0 in there. What do I get? Why did it say that? Oh, it says they rounded here, so this would be more than 8 times 10 to the 11th power. I don't know why they did it that way. But anywho, 50 million, we won't plug that one in. It's going to be more than 2 times 10 to the 15th power. That's written in scientific notation. So what happens to the f of x? Remember, that's the output. That's what we get when we plug things in for x. What happens to the f of x as the values of x approach infinity? So our x values are increasing and they're approaching infinity. That just means they're getting bigger and bigger and bigger and bigger, right? What's happening to the y's when that happens? They're getting smaller? They're staying the same? No? They're getting bigger as well, right? Do we have any reason to believe that they're going to stop getting bigger? If we start putting in bigger x's, do we think that the y's are going to stop getting bigger? No. The larger the x value or the input, the larger the y value. So as x approaches infinity, y approaches infinity. We have no limits on what we can put in. We have no limits in the output. We have no limits. There's an infinite number of possibilities. don't understand what. Yeah, but put that up. Put that up. Go put that in your backpack. No, in your backpack. Oh, yeah, no. 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 United's supposed to know she's calling. Alright. So let's try another one. Hey, Madeline, we're going to plug in for the x's here with the x's they give us. So we're going to complete the table using the following function. F of x equals 6 times x minus 1 divided by 3 times x plus 2. But we have a beautiful decimal calculator. We don't have to do any dividing. We're going to start. I'm going to clear all. And we're going to start with the fraction button. Right? So the numerator is 6 times our input. So 6 times 100 minus 1, I believe. Can't see mine. Yeah, minus 1. And the denominator then is 3 times the input, or 3 times the x. 3 times the x, which is 100, plus 2. Everybody good on that? Oh, that's cool. It'll convert it to a fraction for you there. All right. So that, did anybody get something different besides that? That's what you should have gotten. So 1.983443709. Now let's change it to input to 1,000. Just go over here and add yourself a 0 in there in both input spots. So as our x's get bigger, our outputs, our f of x is getting bigger? Yep. Let's switch it to 90,000. Are they getting infinitely bigger? Oh, good. All right. 90,000. So let's see. Did everybody get 1.99998148.2? Patrick, are you on your calculator like I asked you to? We'll come up here to a seat that you can see from. All right, let's put in 900,000. So how are these outputs different than the other outputs within the problem we just got? I couldn't hear you. What did you say? Right. So our last example, when our x's approached infinity, so as our x's were getting bigger, our y's got bigger. And that's happening here too, but our x's seem to have no limit. Our inputs keep getting bigger and bigger. What does it look like the limit to our f of x is going to be? It's approaching 2, but we haven't gotten to 2 yet, right? So that's the question. Are we going to get to 2? So I'm not going to make you guys plug them all in. So if we plug in 8 million, 1 point, and there's 1, 2, 3, 4, 5, 6 nines now, 792. If we plug in 50 million, getting closer to 2, but did we get to 2? 2 billion. So we're never going to get to 2, guys. Right? So this function has a limit. This is kind of like our having that 64, right? It's going to keep getting bigger, but it's never going to get to 2. Like we get half the distance from 64 feet from the wall, and we can get closer and closer and closer and closer and closer, but we never would get to the wall. We never actually get to 64 by having a number, right? So some of the functions have limits, some of them don't. Like this one has a limit. We can see that it's going to approach 2, and that will be considered a limit. Our other example had no limit. So what happens to f of x as the values of x approach infinity? As x approaches infinity, f of x approaches 2. It's never going to get there.
What's the difference between the two?
What?
What's the difference between
These 2 here, or the 2 examples?
2 examples.
So let's look back over here. So these x's are getting bigger, right? Continually bigger. We can put in whatever we want, no limit. When we put in increasingly larger x's, we get increasingly larger outputs, right? And we're approaching infinity. Right? We have nothing that we're limited by here. But here, it's still a measure of infinity, right? But it's the infinity between 1 and 2, right? 1.9 and 2. So the difference is you're approaching not infinity, but you're approaching 2 in the second example.
So if you keep going up, it still won't reach 2.
Still won't be 2. So let's put 4 million in. We'll switch it to that and see.
And it goes into 5 billion.
Oh, it does? So that's a great point. So Ezra just said it's going to put 2, because eventually it's going to round it to 2. But that's not the same thing. There's a big controversy or a big debate among mathematicians, people who that's their area of expertise. Cedric, buddy, put your phone on my desk. Come on, man. So there's a big debate about whether 0.9 repeating is actually 1. So in this case, is 1.9 repeating 2, right? It's above my pay grade. It's above my ability to understand that, right? And one way I can see, yeah, for all intents and purposes, it's exactly the same thing, right? If I got 1.99999 something, I got 2, right? If I got, because we would round it up, I think. I don't know. But anywho, so that's the point of that, Mason. Layla? Yes, because it's being divided. Great point. So like the having, the 62, we were dividing by 2, right? So the difference is that this one has a denominator, right? It's being divided. So there's a certain function that's used in mathematics to explain this concept of limits and infinity. As values of x approach infinity, f of x approaches what is called the exponential base. Also above my pay grade and math skills, really, but what I love about the exponential base is that it's a button on our calculator, right? We have a formula that has the exponential base in it. It's a thing of beauty. We can use it to compute continuously compounded interest. So that button on our calculator, everybody go to your calculator. Everybody go to your calculator. Madeline, everybody go. I know, but you're not looking at it, honey. You had your head down. You can't see. Go to this function. This is the button we're using. E raised to the x power. That's the exponential base raised to some power. We need that button. Okay, so we're going to go back here. Oh, man. I definitely redid that so it wasn't so ugly. What had happened? Anywho, I'll do it again. So this formula that's hard to read on my board should look like this. Okay. I swear I switched it. I must have not opened the newest one. So that is the formula. That's what it should look like. Not this blurry thing that you get. It looks like a pi symbol there. It's not a pi symbol. That's the formula. Now, what do all these letters stand for? What do you think the P stands for? Hint, we've used it before. Principal, and they call it the beginning balance here, but it's the same thing, right? Initial value, beginning balance, principal. What do you think the R is? As a decimal. What do you think the T is? Time in years. Yep. So these are not new things, right? This one, just another way of saying the ending balance. This is our exponential base. This is not a variable. Let's make a note. This is a button on the calculator. You're not going to be plugging in a number for it. So don't try to find the E in a word problem and plug in for it. It's literally a button on the calculator, okay? So far, so good? So the ending balance is equal to the beginning balance times the exponential base raised to the raised times the time. That's what that says. If we deposit $1,000 at 2.3% interest compounded continuously, what would your ending balance be to the nearest cent after 5 years? So when you're on a test, this is your hint as to what formula to use. Okay? You have to know if it asks for the ending balance, it's asking you to find the A. Okay? One of the things that as a group you're not great at yet is finding the rate as a decimal. Let's start with the easy part. The A is what we're looking for. The principal is, what's the principal? Sorry? $1,000. Now the rate, can anybody tell me what the rate is? 0.023, that's right. So a lot of you are putting 2.3, right? It's not 2.3. Remember, to get the rate as a decimal, you take the percent, get rid of the percent symbol, and divide by 100. If you do, you're going to get 0.023. The time, pretty straightforward, is 5. Compounded continuously, we're not looking for an N, the number of times compounded, right? It's different formula. So you're just going to plug in. Not for the A, that's what we're looking for. The P, not for the E stays at E. The rate and the time. We're going to go to our decimal calculator, we're going to enter it. You do need those parentheses around that rate and time on the decimal calculator. So everyone's going to the decimal calculator right now. Clear all? We don't enter the A equals, you just enter the numbers. So 1,000, this is 1,000 times this, but you don't have to put in the times. Just go to the function button, hit your E of X, so E to the X power. You can use the buttons on your keyboard, you can use the buttons on the calculator, it doesn't matter. Like here, I can go back to the main and get my parentheses, or I can use my parentheses on my keyboard. 2.023, and you can use the asterisk on your keyboard for multiplication. You don't have to go back at all. You have a question, Madeline? Okay. So the ending balance. Now, here's something that, as a group, I just read your quizzes and push them to focus. I went back through giving partial credit. Sadly, I did give partial credit even for kids that had A's because it's not rounding correctly. So we're going to review again how to round, especially to the nearest cent. The nearest cent is always the second place from the decimal, second place to the right. So in this example, the cent is, the decimal place that represents the cents is 7. When you round, you only have two options. That number, if we're rounding to 7, it can stay a 7 or it can go up to an 8. Those are our only two options. Can't go down, right? So if it stays a 7, we get rid of everything to the right. If we move it up, bump it up to an 8, then we get rid of everything to the right, right? How do we know? Well, whatever number is directly to the right of that number we're rounding to. So if this number is 5 or greater, then that 7 will go up to an 8. But if that number is below 5, then that number would stay a 7 and we get rid of everything else. So that's why this rounds to $1,121.87. I'm not trying to insult any of you. There are a ton of you that I gave partial credit for not rounding correctly, all right? I have no idea who. I did not judge, but I'm telling you, I want you to be able to do that. Kamara, will you drop your phone in your backpack for me, please? Okay. Let's go to our next example. So here, 3 different types of interest we're looking at. Simple interest, compounding daily, compounding continuously. These tell us which formula we're going to use. Kid, will you put it in your backpack, not your pocket? So simple interest tells me I'm using that formula. Compounded daily tells me I'm using this formula. Compounded continuously tells me I'm using this formula. So that's really the most important thing you have to be able to do. You have to be able to look at a problem and go, okay, I need to look for this formula. Okay, I need to look for this formula. You need to know what parts of the formula are represented here. So in number 1, it says they're going to deposit $10,000 at 1.85% simple interest. What would your ending balance be after 3 years? So you should be able to tell me, what is the principal? 10,000, right? So that's the principal. What's the rate? Very good, 0.0185. What's the time? Right, that's the time. So we didn't write it out, but we marked it on here. Plug it into this formula. So notice it says I. This doesn't say ending balance. This gives us the amount of interest. In order to find our ending balance, it's got to be our principal plus our interest. So the ending balance here, you have to know, is the principal plus the interest, right? So the interest, you plug this into your Desmos, you're going to get $555. Add $555 to the $10,000 principal, so now we know after 3 years, at this rate, $10,000 deposit, your ending balance will be $10,555. So this compounded daily, so we've got different parts of this formula that we have to recognize. Is the P the same as the P here? Is this P and this P the same? Liana, what do you think? The P here and the P here, do they represent the same thing? Yeah. They do, right? So if our principal is $10,000 here, or the deposit is $10,000 here, those are the same number. Is the rate the same? 1.85%, and that's 1.85%, so can't we use 0.0185 again? Okay. What does the N stand for? this is something you have to know. If you're using this compounded daily formula, you got to know that the n represents the number, how many times it's compounded in a year. So daily, you have to know that the n equals 365. So that's different. So we're going to type that in. The time is still the same. If you're entering this on the Desmos calculator, what are you plugging in? Our A is our ending balance. P is 10,000. Left parentheses 1 plus our 0.0185 divided by 365, all raised to 365 times 3. So if we put that in our calculator, $10,000, left parentheses, 1 plus. Now onto our fraction, so I'm going to use my fraction button on that main screen. I'm going to enter my rate. I'm going to enter my n. I'm going to close my parentheses. Get out of the denominator first and then close my parentheses. I'm going to raise it to this power, so I need a to the b. I need left parentheses, 365 times 3, and close my parentheses. So now I have to know, it asked for the ending balance. It did not ask me to find the interest. It only asked me to find the ending balance. So that is what this formula represents. So one more time, we need to go over this rounding thing, though. All right, so here, 7 is in the spot we're rounding to. Because this is a 5 directly to the right, that means that goes up to an 8. So that's why it's rounded up to an 8. We just did this one, so I'm not going to plug it into the Desmos with you right this second. Our principal is the same. Our rate's the same. What's the only thing that's different here? Our time's the same. What's the only thing that's different? The formula is different. What part of the formula is completely different? The E, that exponential base, remember, just a button on the calculator. So what I've uncovered on all these things is whatever typing into the calculator. Remember, that's the work you show me. What did you put in the calculator? Devian? You want to tell me what you got? Yeah. What'd you get? Is that why you're raising your hand, Betty? What were you raising your hand for? Oh, I thought you were raising your hand. $10,570.69. Same principle, same interest rate, a different way of computing the interest. So, how much more did they count that was compounded daily earned than the simple interest? How do you know? How much more? Just means to do what? Add, subtract, multiply, or divide. Subtract. So we're going to take the compounded daily, $10,570.68, and subtract $10,555. 1568. Continuously compounding, daily compounding, only 1 penny apart, right? FYI, that's how you write 1 cent. 1/100th of a dollar.
Morgan Hill, please come to attendance. You are being signed up. Morgan Hill, come to attendance.
So, put this one in your calculator. I think this is the last one, right?
Yeah.
All right, so we're going to do this before the bell rings. The principal, $4,700. The interest rate, 0.0103. The time, that's what we're plugging in.
Top line goes back up. Oh, shit.
I think that's right. One of them had a mistake on that.
Tonight.
Can y'all stop talking while I'm still talking, please? Oh, I did something wrong. I love that I can look over here and see what I did wrong. So we're rounding to the 4. Look to the right. It's a 7, so the 4 does not stay a 4. It goes up to a 5. That's why we round that to 65. All right, do your worksheet. If you've not done that Nearpod, do it. If you didn't do yesterday's worksheet, do it. Get it turned in. Don't take anything after the day of the test that it covers, the test that covers it. Have a great weekend.